The live stream, we're still on speaker view, should be good to go. Oh my goodness. Now it's time to start talking about test questions. And I should do the same thing to you that I did to the other class. I'll mention a couple things that are coming for the next time. That way you can read about that after Monday's lecture. Still waiting for this to hit the pause button here. I'll get your question, I swear. It's taking so long. Now it's time to start talking about test questions. There we go. All right, so I wanted to mention just a couple of quick things that you can read about next week. Right? Does anybody remember Gauss's law? What was Gauss's law? Remember that? Or sometimes it was EA equals, you remember that? And if you recall, this came from the integral of E dot dA was equal to the electric flux, right?
Are you able to zoom in on that?
Oh, yeah, thank you.
Thank you.
My bad. Thanks for the reminder. That was Gauss's law. Well, there's going to be a new thing called Ampere's law. And that's what we're going to talk about next Wednesday. This is still in chapter 29. So then you can worry about the homework for this class after the next test. But Ampere's law is similar, but not exactly the same. It's BS equals mu naught I enclosed. All right. And so the equivalent here would be BS equals mu naught. What's the integral way to determine current? You remember that from chapter 26? JDA. Remember that? So we're going to finally start using that current density, right? And similarly, now it turns out magnetic flux, this is where the two differ, right? This is electric flux down here. It turns out Gauss's law relates to electric flux. Ampere's law does not relate to this because this is Tesla times meters. S is an arc length. And I'll show you an example in a minute, but the idea of mag flux, magnetic flux, that's still the integral of B dot dA. So it turns out Ampere's law is a little bit different. Here we had areas all the time. S is an arc length. And so if I could show you something here, we're going to do this all next time. You don't need to take notes on this, right? Imagine we have some Amperian loop instead of a Gaussian surface. There's an Amperian loop. Has a length S. In this case, do you agree S equals 2 pi r? And then what could we do? I could build this up out of thin shells. Remember this? And the idea is, well, here, the area of the shell, dA would equal 2 pi r twiddle dr, twiddle, where this distance here is r twiddle. This is like the least centered circle. But then you could just turn the crank and J, does anybody remember how you figure out J? I total over area total. And there's Ampere's law. We've in theory covered it now. I bet when you look at this, it looks vaguely familiar, right? The trick is getting used to these new symbols. We're going to discuss this next Wednesday. After class on Monday, when you finish your test, if you want to do homework or read about it, you can try and read the book and then come to class ready on Wednesday to discuss Ampere's law. All right. And we can discuss magnetic flux and why it's not quite the same as Ampere's law next time too. We'll talk about things called solenoids and toroids and different ways to get magnetic field both inside a wire and outside a wire. All right. Test questions. Anybody got them? Anybody that wants to leave is welcome to leave. Anybody that wants to flake out on Zoom, flake out. It's not flaking out if it's okay. But if you have questions, we can talk about it. You can just look at a random test question that looks too hard for you and say, how do we do this one? I'm cool with that. 28.20 was the workbook question?
Yeah.
Okay, we're gonna look at 28.20, everybody.
George said, did you start the second live stream?
I believe I did, yes. Thank you for checking. Thank you. I appreciate it. 28.20. Ha 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 ha. Okay. Yeah, I like that one. This was an old test question, so this is a good one to ask about. It's also one students tend to flail about. All right. I love this one. I love all these problems. Oh. That is a problem, all right? And that problem is 28.20. Okay, looks like we got a coordinate system here. That's always nice. I hat, J hat, K hat would be the page done. All right. What's sitting on there? A cylinder is sitting on here. Everybody agree that's supposed to be a cylinder? Now there's some coils on it. Like this. So this is kind of hard to see already. Do you agree? We're looking at a cross section. I'm looking for something cylindrical. Now G to the rescue. Right? This is my cylinder sitting on there. And the idea is I'm wrapping some coiled wire around there. Got it? Okay. The top face of the plane is a magnetic north pole. So, right, we're saying this is a north pole here. And this is a south pole down here, right? So this, right, we basically got a bunch of magnets like this sitting under this thing. Is everybody okay with that? What it says. What does that piece of information tell us? Telling us that this top surface is a north pole tells us something. What does it tell us? The B field goes out of north. Now in this problem, this is the external field, right? Clearly we have our coil here, but we're not worried about the magnetic field created by the coil. That's chapter 29. This magnetic field is external to this coil. It's created by something external to the coil. So that's why I'm calling it B external. All right. So we know the cylinder radius, height. What else do we know? Mass. Do we know the number of turns of the coil? Right? By the way, whenever you see this kind of thing, a quick way to think about it is, isn't the effective current just multiplied by N? The amount of current times the turns is the effective amount of current. This is one way you can multiply the current, right? You can either use a car battery like we did, or if you just make a bunch of loops, you should get the same amount of current looped a bunch of times, effectively makes a larger current. All right. Cylinder is released from rest and remains at rest. What? Cylinder remains at rest upon its release. Part A, determine the magnetic moment. Okay, somebody tell me, when it says determine magnetic moment, what's the symbol? Mu. Is it a vector or is it not a vector? Magnetic moment is a vector. Magnetic moment magnitude is a tongue twisting scalar. Okay, now what is the magnetic moment equation? You were saying it. NIA vector. Huh. Well, N and I are known. All we have to do is figure out the area vector. What's the area? We want the area of the loop. Do you agree? Is the area of the loop going to be pi r squared? Is it? No,
The area of a cylinder.
it's not. It's this area here.
Rectangle then?
It's a rectangle. Do you agree? Right? Think about this. The wire's coming up here, then along this axis, then down, then around. I believe 2RH was right. If I could draw this thing on its side a little bit. It might look a little bit like that. Do you agree? And the idea is the coil is going around like this. You know what I'm saying? So it's a rectangle. And what's this height here? That's our 2R, and this must be H. So what is mu? We need a direction, don't we? How do you figure out the direction? So this is the magnetic moment magnitude, but that's not the magnetic moment. We still need the direction. How do we figure out the direction? What?
No.
Oh, what were you thinking?
I was thinking
I promise I won't make you walk up here.
of.
This time.
I was gonna do like the way the current is flowing, kind of, like your head type of thing. but I
Yeah,
don't know.
yeah. So, okay, so there's a right-hand rule involved, agreed? What's the right-hand rule for direction of mu? Curl fingers of right hand in direction of current. Then what? Or I could say it points mu hat, right? All right. Well, which way is current flowing? Darn it! We don't know, but I claim you do know, or can figure it out. Huh? Any ideas from anyone? Zoom land. Any ideas out there? What are your thoughts, Zoomers? Or in-personers? Anybody? What are my choices? Aren't there only two options here? Look at it. Current, which way could it flow? Here, up or down, right?
Yeah.
So what are the choices for mu? This way or that way. So it's either this way,
Higher negative amount.
it's one of these two. That's my claim, right? Because that's the only possibilities. So which one's right?
Well, there's a force holding it up.
Oh, yes, that's the right piece of information to use. Do you agree the natural tendency would be to roll downhill? So we know that the magnetic moment must be such that it opposes rolling downhill. That is a correct statement. Does that feel good? So which way does it have to be? You want to say this way? Well, if it was this way, what would it tend to align with? This is a little bit like, remember, the magnetic moment points kind of like it's a north pole of a bar magnet. So think about this. Mu is a little bit like We know this now. Do you remember B at the center of a coil is mu naught I over 2R, right? What's the direction of it? Right-hand rule. It's the same right-hand rule. Do you agree? Well, the idea here is this coil is acting like that kind of magnet. Now here it's not a circular coil. So do you agree this formula is wrong? This isn't, but it's approximately like this, right? If it was a circular coil, that might work. And there's missing an N and some other factors, but whatever. The idea is this is the magnetism created by the coil, direction. Or this is the direction. Which one makes sense? What do magnets tend to do? Relative to an external field. You put a magnet next to another magnet, what do? They snap together. Well, let's try it. Let's say this is one of the magnets. Here's the other magnet. Which way would it snap? Which way would this one go? Is that going to keep it from rolling downhill? No. What if it was right here? It would try to roll uphill. Gravity would oppose it. So that means mu must point this way. Now let me look at the picture. Yeah, mu is this way. You agree? Isn't that? This is why people hate this chapter. All right? But I love it. So which way is current flowing? Up or down right here? Up. All right. Think. It's either this way or that way. If it goes this way, it would try to align with the external field and it would try to roll uphill. That's what we want. We need something to balance gravity, which is trying to make it roll downhill. Is that what you needed? That's the hard part, right? So in this case, what's the question mark here? Oops. That is the magnetic moment vector. Feeling it? All right, all right. That was part whatever. A. That's pretty tough, isn't it? Now, of course it's tough because we haven't done a lot of these. I think we only did 1 or 2 of these last time in class. So this is like your 3rd one. So now after this, you should get a little faster at it, hopefully. All right, what's part B? Okay. Oh, so we're trying to figure out what? What is part B asking us for? What am I trying to find in part B? I'm trying to get B, external magnitude. That's what it's asking in a fancy way, right? What B external, that's the magnetic field magnitude, is required to keep the cylinder at rest. Now, Christian, what were you suggesting we do? Sum of torques. What are the torques in this problem?
Friction.
Well, how about this? What did we usually do in physics 161 when we want to analyze a torque problem?
Yeah.
Draw an FBD. All right, let's draw the FBD on the other whiteboard. Board 6. So I'm going to draw this thing. There, here. We know that this angle down here is theta, agreed? And this is in the way. So let's get it out of here. All right. Anybody who wants, tell me anything. Something. Give gravity. Where does gravity act? At the center? You're telling me that's pretty close to the center. There's gonna be a gravitational force, right? mg. What else we got? Anything else? Friction. How do I know there's friction? What would happen if there was no friction? It would just slide. It wouldn't matter how much torque you provide because it wouldn't grip the road. Right? So where's the friction? Okay. Friction up the plane. What else we got? A normal force. Do you agree this doesn't fall through the plane? Normal force, perpendicular. That's its definition. Notice I use lowercase n for normal force. Some people use F subscript n. That's fine too. But I like to use lowercase n for normal force, capital N for the units of force, newtons. All right. All right. Any other forces? Okay, there's mu is not a force, but so we're going to do a modified FBD. This is not really an FBD because I'm drawing something other than forces. Mu is a magnetic moment. It has its whatever units it has. But was mu this way?
Yes.
Thank you. All right. What else do we have here? I'm going to draw the B field. Do you agree? And I'm gonna, you know what, on this one, since we're drawing magnitudes and directions, I'm gonna take off this. So the idea here is the direction is indicated by the arrow and the magnitude is indicated by the symbol, right? So this is kind of like our normal physics, whatever class that was. One. All right, now, Christian, you said something. What did you say again? Oh, what are we trying to balance here? The forces?
Yeah, so torque.
The sum of torques is what matters for rotation, agreed? We could try and do sum of forces, but that's not going to help us with this magnetic moment, right? Do you know any equations for force that have magnetic moment in it? No, but we do know one that has torque in it, right? So that's a bad idea to do force. We're going to try and do torque. So what do we know about the sum of torques? I agree, the sum of forces should be 0, but what about the sum of torques? It's also 0. Do you agree? It's not rotating? So, and even if it was rotating, as long as it's rotating at constant speed, we could still say torque 0. But in this case, it's rotating with constant speed 0. So alpha equals 0. All right. Well, what are the forces that cause the torque? Where is the pivot point? Okay, we usually think of doing the center as our pivot point, right? Now, to be clear, do you agree this is not rotating about the center? Do you agree it's also not rotating about this point? So then it becomes a little bit tricky. For me, it makes sense to use the center as the pivot point here. Right? The reason I'm thinking about that is that makes sense for me in terms of this magnetic moment and B external torque. Okay, so I haven't thought it through. What would happen if you put this down here? Would it still be the same? I don't think so. So I'd have, right, because then there's a parallel axis and I'd have to think, and I'm like, oh, I don't know. So for me, I'm going to use the center as the pivot. So what are the terms that cause a torque about the center? Well, there's torque due to B external. Agreed? What else? Friction. Anything else? Does the normal force cause a torque? Why not?
On the. No, it's straight. Normal.
Line of action through pivot. Remember that? If the line of action runs through the pivot, no torque. Right? How about mg? Line of action through the pivot, no torque. All right. That's it. What does that tell us about these two torques in terms of signs and magnitudes and things like that? Opposite in sign, equal in magnitude. So we could just say, notice the subtle difference here. We could just say torque 1 equals torque 2 in magnitude. Or I could say the vector sum is 0. See the subtle difference? You either set the magnitudes equal or say the vectors are equal and opposite. Well, let's just do this here. What's the torque due to B external? Magnetic moment crossed B external. We've gotten B external involved. That's what we're looking for. I'm feeling pretty good. What's the frictional torque in this case? What's that? What's the general expression for torque? R cross F. This looks great, but means nothing if you don't know what the symbols mean. So tell me what the symbol R means physically. From pivot to, I'll say, point where force is applied, because that's the words I like to use. From pivot to force. Notice this is a little bit different R than from source to point. But it's a different equation. R has a different meaning. From pivot to point, force applied. That's the definition. Help me. What is R vector for the frictional torque? Somebody other than Christian. We're going from the pivot to the point where it's applied. What's that? Now careful, I just want the R vector right now. And actually, do you agree that sometimes we write this as RF sine of some angle? So just tell me what's R. Yeah, it's just R. But big R in this case, because big R, it's just the radius. What's the force? Friction. What's the angle I should use for the friction? Do you see a 90-degree popping out there? Oh, shoot, but I don't know what the friction is. Wait a minute. Could I find the friction some other way? How could I do the friction? Sum of forces. How about I do parallel to the plane? What's one force parallel to the plane? Mg sine theta. Do you see it? Because if this is theta, if that's theta, this is 90 minus theta. That makes this theta by these whatevers. That's also theta. Do you agree? That's a very technical whatever rule. Sorry. But do you agree that it's mg sine theta down the plane and friction up the plane? So doesn't that tell us friction equals mg sine theta? So now I got something to plug in here and I can solve for B external. Help me out. What's mu cross B going to be? Whenever you have a cross product, it's always this times that times angle between, right? Well, that's going to be mu B external, B external times what? Sine of what? Yeah, do you see if this is theta, this is a right angle, isn't this 90 minus theta? Well, what's sine of 90 minus theta? That from Remember that from whatever? I'm tired. You are too, I'm sure. What do you think? This was probably the best problem to review right now. Wise choice. It took us the whole time, but we talked about a lot of stuff in here. We talked about forces, we talked about torques, we talked about angles, we talked about magnetic moments. Pretty good freaking problem. That's why I put it on the test. And remember, this one's all in the solutions. I put big ass pictures in there. I killed myself on this chapter. So you want to see what it looks like? I'll bring it up. And then I'm not going to erase anything. That way you know if you want to take a photo. How about you Zoom people? You Zoom people. What do you think? Any questions, Zoomers? Did you see that?
I don't think there's any more time.
Yeah, there's not any more time. But were you able to see everything okay?
Yeah, I saw everything. Okay.
Okay, all right. Did you have a quick question? What was your question?
No, I don't think so. Nothing like specific.
All right. I'm gonna make sure I have this solution here for that problem. What problem was this one? 28 point something, 20? Okay, control F, 28.20. I'll find on page, all right, geez. All right, let me do it up here. Good one, isn't it?
Yes. I think on the exam you had the same one, but you changed the poles.
I changed the field direction. You could make this one tricky by saying the field is straight up instead of angled, or you could angle the coil, or you could angle the bolt, or yeah, you could switch the angle downhill but yeah, if it helps, Jesse, did you want to come take a look at this really quick?
Yes, I'm pretty sure it's basically the same. It's just some of the
Oh,
other.
that's what you were looking at?
It was supposed to be, say, it was like size stuff. Yeah.
And I did it right there, and there, and all that.
That was the only part I really needed was I forgot the trig part, I always forget.
Yep. Turns out, by the way, you could have used the other pivot, the instantaneous pivot. And so in this problem, because it's at rest, you could use either pivot, right? And so I think in the end, what you would have gotten is radius times mg sine theta, because only a component of the mg would actually cause the force, would equal mu cross b. You see it? You go from this point up to that one. So the radius vector would be the same, but the amount of force is mg, and then there'd be a sine theta in it. So notice we're getting that same equation, whether you use the instant pivot or that pivot. Either one would have worked. So, all right, anyways. Cool.
Practice.
Yeah, we'll see you in lab tomorrow. Be ready to rock. Oh, just roll? That's cool. Well, I'm going to apply a large magnetic moment here, and that might prevent the rolling. That's so dumb. Yeah, that's very good. That's very good.
Is there anything we need to prep for tomorrow or anything?
If you want, I'll probably send something tonight, if I remember when I get home.
Yeah,
Just telling you, like, I sent it out last week, but people lost it because that was a week ago. So I'll send it out again.
Yeah, I know the solenoids and stuff like that. I already started reading.
Yeah, and you've got what are you doing? Solenoids? Yeah, so, yeah, I've got some old school videos somewhere. I'm not sure where. And I literally made videos of me doing stuff like this, and maybe I'll try and send that as well. So you can kind of get a feeling for it.
Exactly, that's
But at
all I
this
want.
point, it's just come in and be ready to work.
That's what I kind of figured, but I just I like to be prepped for it. So I know
Yeah,
what to know.
yeah. I'd
So,
read the manual.
Yeah, I already did that too.
Yeah. If you want, you could prepare a shell presentation. Right? A PowerPoint. Just like
Oh,
do
yeah,
this-
yeah,
do
yeah.
the stupid stuff, right? It's just white background, black text, one font. Have your fonts picked out. Maybe like think about what's the question you're trying to answer. And if you just do that, you'll have something to hit the ground running. Like, what am I trying to do?
Perfect.
And if you're doing solenoids, it's B field along axis and in the plane.
Correct, yes. Okay.
Also, ours is the same one, running off the same thing. then.
We solenoids too? or-
No, it's on the same section,
Oh,
because it's like a one.
How about you guys?
Lab section.
Okay.
That's why it's called a 1, 2,
All right.
4.
I got.
So these are all basically doing the same.
Helmholtz coils. So that's basically two coils instead of one.
You're
And
with-
so, right, what can you do? Figure out the B field along the axis. How about, so for you, you're doing Helmholtz coils.
I'm pretty sure he was on notes for a reason.
Here's the
No, no,
problem with
I mean,
Helmholtz coils is this problem, 29.19. So
Yeah,
if
you
you
got it.
wanted to do
Yeah.
something before,
Mhm.
you could like look at this problem and get a feeling for it.
Mhm.
And just have the solution, follow the solution. Don't try to be creative and think it through yourself. Just kind of say, oh, what the hell's going on here?
Right.
And then, if you spend 15 minutes going through the solution, you'll have a better idea of what the answer is supposed to be. You gotta basically figure out how to put this in Excel and plot it. That's fine, right?
Yeah.
And then you're gonna have to actually measure it.
Mhm.
So in this problem, you agree C is like the distance.
Yeah.
So the idea is you're gonna have a sensor and go along here and measure the B field.
Mhm.
And then you're gonna see if that matches up with theory. It's okay, right?
Okay.
And then what you're gonna do is in this problem, you'll notice that you can pick, this has an arbitrary spacing D.
Mhm.
So what you're gonna do is you're gonna try it close together, farther apart, et cetera, and see if it matches what you expect,
Okay.
right? And so this formula, basically D is sometimes gonna be the radius of the coil, sometimes it'll be 2 times the radius of the coil, sometimes it'll be half a radius, sometimes it'll be 0, and it'll be right next to each other.
Right.
Right?
And then hopefully what you can do is learn how to do this really fast.
Okay, I'm not good with
Right?
this, bro.
Cool.
Yeah.
And so tomorrow it's just data.
Right.
Next week it'll be
Yeah.
compare.
Prepare, and then the week after is present.
Yeah,
Okay.
but it's gonna be a lot easier to check your work. Like you could try and code this out in Excel, right? See if you can figure out how to set that Excel sheet. up.
That way, like, we can post
If you
it
want.
around.
Right.
Cool.
And then.
All right, yeah.
Also, another quick question. I've heard from other people, like, I'm not sure, are you gonna use, do you have current density on the exam? Or will you leave it
You know,
Hey, we're just like.
the only way I would use it is J equals I over area. I'm not gonna do integrals. with it.
Right.
Yeah, that's it.
Okay.
That's it. So do I have that on here?
I don't think you did, because me and, there's a problem.
It's not my intent to put a lot on there.
Yeah.
The only way I think about it is every once in a while, I'll show you the only type of problem that might show up. It was this one. This one. Oh, yeah, see here I say the current, right? I could say the two wires have the same current density, right?
Right.
That's the only way I could imagine that. 26.6, but what if it was the same current density? Well, then all you have to do is just say, to get current, you just say J times A.
Mhm.
Good?
Okay.
I'm not trying to screw people over, and I don't think I used it at all on this year's test.
Okay.
But yeah, that's the only way I could think of it is in 26.6. I might say J instead of I.
Okay, yeah, because it was on an older exam. I thought I heard different.
Yeah.
information, so I just wanted to
Yeah,
make sure.
generally speaking, I don't focus on this test, I focus on this test.
Okay.
Right, you saw that it's gonna appear in Ampere's law.
Okay.
That's usually where we use it. Cool?
Okay, sounds good. Yeah.
Yeah,
just wanted to make
yeah.
sure.
Yep. Good.
You have a good night.
Yeah, you too.
And I want to make a correction, the batteries for Costco, not that they hold a larger charge, as they could jump system, stronger system, I guess.
Oh,
I think
they
that's what
can
it was.
release more charge instantaneously.
Yeah, like, because I was thinking about that, I was like, there's no way they could hold more charge than this,
Right.
but still,
But yeah, so maybe they have less internal resistance.
possibly. I haven't done a lot of like research on it, so.
Yeah. Every battery has internal resistance. So
Yeah.
if you, as the technology improves, usually you can lower internal resistance.
Uh-huh.
And so that effectively allows you to emit more charge around the circuit faster.
Or they allow you also to hold more charges, or is
No,
that just
no.
different part of the
So
system?
storing it is one thing,
Uh-huh.
and then releasing it is another, right? Total charge stored is Q.
Yeah.
Right? And then maximum current flow relates to internal resistance, right? E over R.
Yeah.
So in this circuit, probably the dominant resistance is the internal resistance of the battery. That's what's limiting the circuit, however much resistance is inside the battery itself. So that's the difference, right? Newer batteries probably have lower internal resistance if they are designed in a smart way or something.
Yeah,
Cool?
yeah.
But I don't know.
Well, I don't know, like
I suspect it's.
Like
what it
I've dealt with these for so long, I never understood how they work. I just know what they can do.
Yeah,
So I'm saying-
usually you have plates inside and acid, right?
Yeah.
But now, like, that's the old wet cell battery, and I'm assuming they're still that way, because they worked for a long time.
I don't think I've heard about them changing. Maybe like
They have
the,
acid in them, right?
yeah,
Right, and so the
Yeah,
acid, you don't want it to
changes.
leak out. Right, so that's why they're sealed in this plastic, but over time it corrodes the terminals, right? You get that, right? And so, yeah, I don't know.
some people just, I don't know why, but have you ever worked with the batteries a lot? Like when you had to change the acid out?
I've never changed the acid out.
Oh, okay, well, some people
That's
are
old school, right?
idiots, but like
Oh.
they get like a flathead, they pop off the top. And I'm just like,
Sprays
why
everywhere.
do you do that?
Oh.
They're like old school, they're just like, that's what they do. That's how they protect their eyes. I'm like, no, good.
Yeah, I mean, if you have safety equipment, you could do that.
Yeah,
Like if you've got a full face shield, right?
well, that's usually what I would do. Like I would have my uniform on, have my face shield on, and I
Gloves.
just pop it off, drain it, then exchange it. It's like, was that so hard?
Yeah, yeah, exactly.
Yeah,
Well, it's same thing with power tools, right? Sometimes people won't pay attention when they're using power tools, they want to use safety, but it only takes one time for a stray windshield to go in your eye to make you blind.
yeah.
So why wouldn't you put on safety?
Some people are just lazy about it. I feel.
Yeah, they're
Or they just, they
overconfident.
don't care.
They haven't seen it happen 10,000 times.
Yeah,
Well, the 10,000 at first could be your lucky day, right?
yeah.